Everyone grows up seeing the same solar system map: 8 planets. The sun in the center, clean and complete. But that map is wrong. Not slightly wrong in scale. Wrong in scope. Because right beyond Neptune lies the Kuiper Belt, a frozen wilderness billions of miles wide, older than any planet, holding more secrets than everything humanity has ever explored. Most people have never heard of it, but it's there, and it changes everything. Now, let's begin. Ask almost anyone where the solar system ends, and they'll say, Neptune. It's a reasonable answer. Neptune is the 8th planet, the last one on the list, the final dot before the emptiness begins. Every diagram confirms it. Every school poster shows it. 8 planets arranged in a neat row, and then nothing. Just black space stretching forever into the unknown. That belief didn't come from nowhere. It was built over centuries of careful observation, refined through generations of textbooks, and reinforced every single time someone looked at a solar system diagram and saw Neptune sitting alone at the edge, like a period at the end of a very long sentence. The model felt complete, tidy, finished. And for most of human history, there was no reason to question it. It isn't finished, not even close. The idea that Neptune marks the boundary of the solar system is one of the most widespread misconceptions in popular science, not because scientists got it wrong, but because the public picture of the solar system never kept pace with what scientists actually discovered. Neptune was confirmed as the 8th planet in 1846. For decades after, it held its place as the apparent frontier of everything. Then, in 1992, astronomers David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, detected a faint reddish object drifting beyond Neptune's orbit. It was small, it was cold, it was slow, and it was designated 1992 QB1. It wasn't alone. More followed, then hundreds more, then thousands. The edge, it turned out, wasn't an edge at all. It was a doorway into something far larger than anyone had mapped. What lies beyond Neptune is called the Kuiper Belt, and it fundamentally rewrites the geography of everything we thought we understood about this solar system. Here's a way to feel how wrong the old picture actually is. Imagine the entire solar system scaled down to the size of the continental United States. In that model, the sun sits at the east coast, say, New York City, Mercury, Venus, Earth, Mars. They're all still within the greater New York metropolitan area, clustered close to the starting point. Jupiter gets you out to Ohio. Saturn reaches Indiana. Uranus is somewhere around Missouri. And Neptune lands roughly at Illinois, Chicago, give or take. That sounds far. Most people would stop there and call it the edge. But the Kuiper Belt doesn't start at Chicago and end there. It starts at Chicago and extends all the way past Denver, past Salt Lake City, past the Nevada desert, stretching nearly to the California coastline. Half the continental United States remains blank, unmapped, unrepresented in the version of the solar system that most people carry in their heads their entire lives. Half a continent of space, simply missing from the picture. The actual numbers make this even harder to hold in the mind. Neptune orbits the Sun at an average distance of approximately 30 astronomical units. 1 astronomical unit, 1 AU, is defined as the mean distance from the Earth to the Sun, roughly 150 million kilometers. Multiply that by 30, and Neptune sits approximately 4.5 billion kilometers from the Sun. That distance alone is so vast, it barely registers as real. Light. Traveling at nearly 300,000 kilometers per second, the fastest anything in the universe can move, takes more than 4 hours just to make that one-way trip from the Sun to Neptune. And the Kuiper Belt begins right there, at 30 astronomical units, precisely where Neptune traces its long, slow orbit. But it doesn't stop there. It extends outward at minimum, based on current confirmed observations, to 50 astronomical units from the Sun, 20 additional astronomical units of space beyond Neptune. That translates to roughly another 3 billion kilometers of territory, not empty territory, populated territory, filled with frozen objects, ancient worlds, and debris that has been drifting in the cold since before Earth had an ocean. 50 astronomical units, 7.5 billion kilometers from the Sun at the outer edge, and even that figure, 50 astronomical units, is almost certainly not the real boundary. It's simply the point where our current ability to detect objects begins to fail. To put Voyager 2's journey in perspective, it launched in August 1977. It flew past Jupiter in 1979. It swung around Saturn in 1981. It passed Uranus in 1986. It threaded its way past Neptune in August 1989, 12 years after leaving Earth, moving continuously at roughly 60,000 kilometers per hour. 12 years of uninterrupted flight through space, and it arrived at the inner boundary of the Kuiper Belt. It had just reached the beginning. If Voyager 2 needed more than 12 years just to reach Neptune, how long do you think it would actually take to cross the full width of the Kuiper Belt? That question doesn't have a comfortable answer, and the discomfort is the point. This is where the cognitive trap reveals its full depth. The solar system diagram doesn't mislead people through dishonesty or bad science. It misleads them through compression, a necessary compression, but a distorting one. If Neptune were drawn at its true proportional distance from the Sun on a standard printed page, the inner planets would be invisible. They would be smaller than the period at the end of this sentence. So every diagram ever published compresses the distances, brings everything artificially closer, and creates a solar system that feels traversable, manageable, and known. But the universe doesn't adjust itself to fit what looks good on a page. The real solar system has an outer architecture that dwarfs everything inside Neptune's orbit. The Kuiper Belt isn't a footnote appended to a familiar map. It is a colossal, largely unexplored region containing frozen remnants from the birth of the solar system, objects that have never been visited by any spacecraft, worlds that exist without names, and distances that no human mission has ever fully crossed. The solar system doesn't end at Neptune. Neptune is where the known part ends, and knowing that distinction changes the entire frame. What we've been calling the solar system for centuries is, in truth, only the inner solar system, the part close enough to the Sun that we could see it, study it, and eventually send machines to explore it. The Kuiper Belt sits just beyond that inner circle, vast and old, and full of things we don't yet understand, waiting to be discovered by instruments and missions that in many cases don't yet exist. Neptune is not the end. In the truest, most literal sense, it is the beginning of the part we don't know. And distance staggering, almost incomprehensible distance is only the surface layer of what makes the Kuiper Belt remarkable. But distance is only the surface of the problem. What's truly shocking is what's actually inside that region of space. The word belt does a disservice to what the Kuiper Belt actually is. A belt implies something narrow, something cinched, a ring of material looping around the solar system like a thin band, the way Saturn's rings appear in photographs. Flat, elegant, contained. That image is wrong in almost every dimension, and it shapes the way people underestimate what they're dealing with. The Kuiper Belt is not a thin ring. It is a disk, a thick, sprawling, three-dimensional disk of material, extending not just outward from Neptune's orbit, but also upward and downward, relative to the plane of the solar system. The vertical thickness of this structure reaches hundreds of millions of kilometers. Objects within the Kuiper Belt don't orbit in a single flat line. They occupy a full three-dimensional volume of space, distributed across a wide range of orbital inclinations, tilted at different angles relative to the ecliptic plane. The belt has real depth, real height, real physical presence in all directions, not just left and right, but up and down, wrapping around the solar system like a thick, frozen cloud rather than a delicate ring. Now consider the total volume that this structure occupies. The space from the Sun out to Neptune, 30 astronomical units in every direction, is itself enormous beyond easy comprehension. It contains the Sun, 8 planets, dozens of major moons, the entire asteroid belt between Mars and Jupiter, and billions upon billions of kilometers of open space in between. And yet, the estimated total volume of the Kuiper Belt, accounting for its radial extent from 30 to 50 astronomical units and its considerable vertical thickness, exceeds even that entire inner region. The Kuiper Belt occupies more sheer space than everything from the Sun to Neptune combined. Pause on that. The region we call home every planet, every moon, every spacecraft humanity has ever launched, every destination ever visited fits inside a volume smaller than just the outer shell of the solar system that most people have never heard of. Within that volume, scientists have confirmed more than 100,000 Kuiper Belt objects with diameters exceeding 100 kilometers. To be clear about what that means, 100 kilometers across is not a pebble. It is not a boulder floating in space. Objects of that size are larger than many US counties, large enough to have their own gravitational influence, large enough to have shaped surfaces, varied geology, and in some cases, as new horizons revealed active processes still occurring on them today. Over 100,000 of these confirmed, cataloged, named or numbered objects. And that represents only what current telescopes can detect at that range. The estimated total, including objects too small or too distant for current instruments to resolve, climbs into the hundreds of millions, possibly higher. The Kuiper Belt may contain more individual objects than there are stars visible to the naked eye from Earth on the clearest night imaginable. Compare that to the asteroid belt between Mars and Jupiter. Hollywood has spent decades portraying the asteroid belt as a chaotic, densely packed gauntlet spacecraft dodging rocks at every turn, debris filling every frame. In reality, the asteroid belt is remarkably sparse. The average distance between objects in the asteroid belt is hundreds of thousands of kilometers. Spacecraft pass through it routinely without incident, because there is simply so much empty space between the rocks that collision is extraordinarily unlikely. But compare the asteroid belt to the Kuiper Belt in terms of sheer scale of content, and the asteroid belt looks like a quiet stream, a gentle, narrow current winding through open country. The Kuiper Belt is the Atlantic Ocean, not because it is denser or more dangerous, but because the difference in scale is that absolute, that complete, that difficult to bridge with ordinary language. And yet, here is the paradox that surprises almost everyone who encounters it. The total mass of the Kuiper Belt is relatively modest. All the material contained within it, every frozen world and every chunk of ancient ice and rock, adds up to an estimated 1/10 of Earth's mass. That number tends to deflate people. After all those enormous figures, after 100,000 confirmed objects and hundreds of millions estimated, after a volume exceeding the entire inner solar system, 1/10 of Earth's mass. The explanation is distribution. Take 1/10 of Earth's mass and spread it across a disk spanning billions of kilometers in every direction, and what you get is not density. You get extraordinary thinness. Individual objects separated from their nearest neighbors by millions of kilometers of absolute emptiness. Entire frozen worlds drifting in isolation, too far from each other to interact in any meaningful way on human timescales. Too far from the sun to receive enough light and heat to drive the kind of chemistry that shapes planets closer in. This is the quality of the Kuiper Belt that resists easy description. Its strangeness doesn't come from what it holds. It comes from the relationship between what it holds and how much space surrounds each piece of it. Something this vast, something this old, something preserved in conditions this cold and this quiet, for a length of time that exceeds the entire history of complex life on Earth by a factor of nearly 1,000. What's strange is that this vastness doesn't make the Kuiper Belt feel majestic. It makes it feel isolating. It makes it feel like the kind of place where things drift away and are simply never heard from again, frozen in their orbits, turning slowly in the dark, unchanged since the solar system was still learning what it wanted to be. There is something unsettling in that, and it's not the unsettling feeling of danger. It's something quieter and harder to name. The unsettling feeling of scale that exceeds comprehension, of ancient things sitting undisturbed in darkness so profound it has no earthly equivalent. But scale is not the most frightening thing about it. Its age is what changes everything. Everything in the Kuiper Belt is old. Not old in the way that mountains are old, or oceans are old, or even ancient civilizations are old. Old in a category that has no human equivalent. Old in the way that the solar system itself is old. 4.6 billion years. That number appears in astronomy textbooks so frequently it starts to feel like wallpaper, like a number you register without actually absorbing. But sit with it for a moment. 4.6 billion years ago, the sun didn't exist yet. Earth didn't exist. The entire structure of the inner solar system, every planet, every moon, every grain of dust that would eventually become the ground beneath every foot that ever walked, was still a swirling cloud of gas and ice and debris, slowly collapsing under its own gravity. The Kuiper Belt formed in that collapse. Same cloud, same moment, same raw material. And then something happened to the objects that ended up in the Kuiper Belt that didn't happen to the material that became Earth or Venus or Mars. Nothing. Absolutely nothing happened to them. The planets formed through a process of violent accumulation collisions, mergers, gravitational compression, radioactive heating from within, intense bombardment from without. Earth's interior melted completely. Its original chemistry was erased, cooked, recycled, restructured. The crust we walk on today bears almost no chemical resemblance to the primordial material it came from. 4.6 billion years of geology plate tectonics, volcanism, erosion, biological activity. Ocean chemistry have processed and reprocessed every atom near the surface countless times over. The original solar system, the raw starting ingredients, are gone from every inner planet, transformed beyond recognition. Out in the Kuiper Belt, none of that happened. The objects there, the Kuiper Belt objects, or KBOs, formed in the same era but were never incorporated into planets. They drifted outward into the cold, where the sun's warmth barely registers as anything more than a slightly brighter star in the sky. And they simply stopped. Not stopped moving, they still trace their slow orbits, completing a single loop around the sun over periods of hundreds of years, but stopped changing, stopped reacting, stopped evolving. The reason is temperature. Surface temperatures in the Kuiper Belt range from roughly negative 220 degrees Celsius to negative 230 degrees Celsius. Those numbers require context to be meaningful. At negative 40 degrees Celsius, exposed skin freezes within minutes. At negative 80 degrees, aircraft lubricants congeal and stop functioning. At negative 180 degrees, the surface temperature of Pluto's largest moon. Karen, in some regions, nitrogen gas liquefies. The temperature of the Kuiper Belt goes far beyond all of that. At negative 220 degrees Celsius, most chemical reactions don't merely slow down. They stop. The kinetic energy required to drive molecular interaction is simply not present. Atoms sit where they were placed. Compounds remain as they formed. Matter persists, unchanged, in a state of near-perfect preservation that no laboratory on Earth can replicate at scale, and no natural environment closer to the Sun can provide. This means that the material sitting on the surface of a Kuiper Belt object today, the ice, the rock, the complex molecules embedded in the frozen outer layers, is, in many cases, chemically identical to the material that was present at the formation of the solar system. Not similar, not derived from, identical. Data gathered by the New Horizons spacecraft and by ground-based telescopes using spectroscopic analysis has revealed what that material actually consists of. The surfaces of KBOs contain water ice, not liquid water, not water vapor, but solid water ice frozen so hard it behaves like rock. They contain methane ice, carbon monoxide ice, nitrogen ice. These aren't exotic substances. They are among the most common molecules in the universe, the building blocks from which everything, including life, is eventually assembled. But on the surface of a Kuiper Belt object, they have been sitting untouched, frozen in place, since before the first multicellular organism appeared on Earth. Then there are the tholins. The word is unfamiliar to most people, but the concept is not complicated. Tholins are complex organic compounds, chains and networks of carbon, hydrogen, nitrogen, and oxygen formed when simple molecules like methane and nitrogen are exposed to ultraviolet radiation or cosmic rays over very long periods of time. They give many KBOs their characteristic reddish-brown color, the same reddish tint that Pluto's surface shows in photographs, the same coloring visible on the surfaces of Makemake and other objects throughout the belt. Tholins are not alive. They are not self-replicating, not metabolizing, not doing anything that biology does, but they are the precursors to the kinds of molecules that, under different conditions, warmer temperatures, liquid water, energy sources can begin to assemble into something that resembles the early chemistry of life. They've been sitting out there for 4.6 billion years, preserved in cold so deep it borders on absolute zero, waiting. Consider what that means as a scientific resource on Earth. If you want to understand what the early solar system looked like chemically, you face an enormous problem. Everything has been altered. Meteorites that fall to Earth provide some clues, but they've survived the heat of atmospheric entry, chemical weathering after landing, and contamination from the biological world around them. The Moon's surface preserves a better record than Earth, but even the Moon has been bombarded, melted in places, and modified over billions of years of cosmic weather. To find material that truly reflects the original chemistry of the solar cloud from which everything was born, you would need something that was never heated, never processed, never incorporated into a planetary body that went through any significant geological activity. That is exactly what Kuiper Belt objects are. They are time capsules, not metaphorical ones, actual, physical archives of primordial chemistry, sealed in cold so extreme that the very concept of degradation barely applies. When scientists analyze the surface composition of a KBO, they are reading the chemical record of the solar system's first moments. Every molecule identified tells them something about what was present in the original cloud, what ratios existed, what compounds formed naturally before any planet existed to complicate things. If the objects drifting in the Kuiper Belt carry the original chemical fingerprint of the solar system undiluted, unprocessed, preserved across 4.6 billion years, then the question they carry inside them is not small. It is not merely a scientific puzzle for specialists. It reaches back to everything, to where Earth's water came from, to where Earth's carbon came from, to where the molecular ingredients that eventually, after billions of years of increasingly complex chemistry, produced the first living cell came from. And that question, once stated clearly, refuses to stay confined to geology or astronomy. If these objects hold the material from 4.6 billion years ago, What secrets are they keeping about the origin of Earth? But that question is only the beginning of what the Kuiper Belt is asking. Because the real question isn't just about where Earth's ingredients came from. It's whether life itself could have started from this place. For most of the 20th century, Pluto occupied a unique position in the imagination, the solar system's lonely outpost. Discovered in 1930 by Clyde Tombaugh, it sat at the edge of the known universe like a solitary sentinel, cold and distant and singular. Children memorized it as the ninth planet. Textbooks listed it without hesitation. The mnemonic devices invented to remember the planets all ended with Pluto, and that felt natural because Pluto felt final. One world, out there alone, marking the end of everything we claimed to understand. Then we found out it wasn't alone at all. In 2006, the International Astronomical Union made a decision that generated more public controversy than most scientific announcements ever do. They stripped Pluto of its planetary status. The reaction from many people was emotional and not without some justification, because Pluto had been a planet for 76 years, and reclassifying something that millions of people had grown up treating as a fundamental fact felt, to many, like a betrayal. School children wrote letters of protest. Bumper stickers appeared. Scientists received angry emails. Some of them still do. But the reclassification wasn't arbitrary. It wasn't petty. And it certainly wasn't because Pluto is small. Though it is, Pluto's diameter is roughly 2,370 kilometers, making it smaller than Earth's moon, smaller than 7 other moons in the solar system. Size wasn't the issue. The issue was a far more fundamental discovery. Pluto is not unique. It is not a solitary anomaly perched at the edge of things. It is one member of a vast population of similar objects. And that population is so numerous, so diverse, and so distributed throughout the outer solar system that granting planetary status to Pluto without extending it to dozens or hundreds of other objects would have been scientifically incoherent. The International Astronomical Union's new definition required a planet to do 3 things: orbit the Sun, have sufficient mass for gravity to pull it into a roughly spherical shape, and this was the critical addition: have cleared the neighborhood around its orbit of other debris. That third criterion is what disqualified Pluto, not because Pluto failed to try, but because the Kuiper Belt itself is the proof of failure. Pluto shares its orbital neighborhood with thousands of objects. It hasn't cleared anything. It is, in every meaningful gravitational sense, a city dweller, not a lone frontier town. The confirmed catalog of Kuiper Belt objects with documented orbits now exceeds 2,000. That figure grows every year as survey programs scan more of the sky with increasingly sensitive instruments. But 2,000 is only what we have confirmed with enough orbital data to say with confidence here is where this object was. Here is where it is now. Here is the path it traces. The estimated total of Pluto-sized objects within and near the Kuiper Belt runs into the hundreds of thousands. There are likely more worlds out there comparable in size to Pluto than there are countries on Earth, and we have visited exactly one of them. A handful have been studied well enough to deserve names and descriptions. Eris was discovered in 2005, and its discovery is directly, causally responsible for Pluto's reclassification. Eris orbits the Sun in a highly elongated path that takes it far beyond the main Kuiper Belt at its most distant. It sits more than 97 astronomical units from the Sun, more than 3 times Neptune's distance. It is not the farthest known object in the solar system, but it is among the most massive. Eris is approximately 27% more massive than Pluto. When astronomers realized they had found something beyond Neptune that was definitively heavier than Pluto, the question became impossible to avoid if Pluto is a planet. What is this? The answer: the International Astronomical Union eventually arrived at was that neither of them should be called planets. Eris was the object that forced the reclassification, and in doing so, it quietly revealed that the category of planet had been applied too casually to an object that had no business being in it. Makemake, named after the creator, deity of the Rapa Nui people of Easter Island, orbits the Sun every 306 Earth years. Its surface is covered in frozen methane and ethane and shows signs of the same reddish tholins found across the Kuiper Belt. It is cold, it is slow, and it is currently classified as a dwarf planet, one of the 5 formally recognized by the International Astronomical Union alongside Pluto, Eris, Haumea, and Ceres. Then there is Haumea, which earns a category all its own. Haumea is the only known dwarf planet in the solar system, with a ring system, a faint, narrow ring of material orbiting around it, detected in 2017 when Haumea passed in front of a background star and its silhouette revealed the ring's shadow. But that is almost secondary to the other thing. Haumea does that nothing else in the solar system does quite like this. It spins, not slowly, the way Earth spins through a comfortable 24-hour day. Haumea completes a full rotation in 3.9 hours. That is extraordinarily fast enough that the centrifugal force generated by that rotation has physically deformed the object. Haumea is not a sphere. It is an ellipsoid, stretched along its equatorial axis into a shape resembling a rugby ball. Its equatorial diameter roughly twice as long as its polar diameter. The spin hasn't torn it apart, only because its self-gravity is strong enough to hold it together. But just barely. It exists in a kind of perpetual compromise between the force trying to flatten it outward and the gravity trying to pull it inward. Quaoar sits slightly closer in and has recently surprised astronomers with its own ring. A ring that orbits at a distance so far from Quaoar's surface that it shouldn't exist according to standard models of ring formation. The existing theory held that rings should only form inside the Roche, limit the distance within which tidal forces would prevent material from clumping together into a moon. Quaoar's ring sits well outside that limit. It shouldn't be a ring, and yet there it is. And then there is Sedna, which deserves its own story, an orbit so extreme, so elongated, so far removed from everything else in this part of the solar system that its very existence suggests the presence of something larger that no one has found yet. Sedna's orbit takes it from a closest approach of approximately 76 astronomical units to a most distant point of roughly 937 astronomical units from the Sun. Its orbital period is somewhere around 11,000 Earth years. Sedna is so far from everything that it barely qualifies as a Kuiper Belt object at all. It orbits in a region that transitions into something else entirely, something beyond even the Kuiper Belt's outer edge. What this catalog of objects describes Pluto, Eris, Makemake, Haumea, Quaoar, Sedna, and the thousands of confirmed KBOs sitting behind them is not a sparse collection of oddities. It is a populated region, a complex, varied, active community of worlds that has been present in the solar system since the beginning, drifting in their slow orbits, each one a different variation on the same theme of ice and cold and age. Pluto is not a lone sentinel anymore. It never really was. It is a neighborhood, and it has thousands of neighbors, and most of those neighbors don't even have names yet. And if this is only what we have found, what remains hidden in the darkness beyond is something no one yet dares to predict. The assumption seemed reasonable. Cold kills activity. Distance kills warmth. And without warmth, without the constant input of solar energy that drives weather on Earth, fuels volcanism on Io, and keeps liquid water moving beneath the ice of Europa, without all of that, What could possibly be happening on a rock sitting 5 billion kilometers from the Sun, where temperatures hover near -230 degrees Celsius, and a single orbit around the Sun takes 248 years? The logical conclusion, held by most planetary scientists before 2015, was that Kuiper Belt objects were geologically inert, frozen corpses of the early solar system, preserved precisely because nothing had touched them, nothing had disturbed them, nothing had done anything to them at all. Dead on arrival, static, silent. That assumption was wrong, not partially wrong, not wrong in minor technical details, wrong in the way that forces an entire field to sit down and reconsider what it thought it knew about what drives planetary activity, and how much of that activity requires proximity to the Sun at all. When New Horizons made its closest approach to Pluto in July 2015, it was moving fast enough that the entire encounter the closest pass. The bulk of the science data collection lasted only a few hours. The spacecraft couldn't slow down. It had no way to brake against Pluto's gravity, no way to enter orbit, no way to circle back and take a second look at something that confused it. One pass, one chance. Everything had to work in those hours, and then Pluto would fall behind forever. What the cameras captured in those hours demolished the dead world model in a single afternoon. The mountains came first, not small features, not gentle undulations in the frozen landscape mountains. The Tenzing Montes Range, sitting near Pluto's equator, rises to approximately 3,500 meters above the surrounding terrain, comparable in scale to the Rocky Mountains on Earth, made not of granite or basalt, but of water ice, which at -230 degrees Celsius is hard enough to behave structurally like rock, rigid enough to hold its shape against gravity over geological time. These mountains had not been sitting there unchanged since the solar system began. Mountains don't form passively. They require internal processes, some source of energy pushing material upward against gravity, reshaping the surface from within. Pluto, 5 billion kilometers from the Sun, receiving approximately 1,000 times less solar energy than Earth, had found some way to build mountain ranges. Then there was Sputnik Planitia. It covers an area larger than the state of Texas, a vast, roughly heart-shaped basin on Pluto's surface filled with nitrogen ice so smooth, so unmarked by impact craters, that the only plausible explanation is that it is geologically young. Not young by human standards, but young in the language of planetary science. Surfaces that have been geologically reshaped within the last few tens of millions of years show far fewer impact craters than ancient, undisturbed surfaces, because fresh material covers the evidence of old bombardments. Sputnik Planitia has almost no craters. Its surface is so clean, it looks like it was poured. And it was in a sense. Nitrogen ice on Pluto doesn't just sit still. It flows, extraordinarily slowly, in patterns that behave analogously to the glacial systems on Earth. Convection cells slow. Churning cycles of warmer material rising and cooler material sinking are visible in the polygon patterns on the basin's surface. Each polygon hundreds of kilometers across. Each one the top of a slow convective column turning in the ice like an enormous kanji frozen gear. This is not preserved ancient terrain. This is active. Pluto's surface is being renewed by geological processes that are still operating today. And then, above all of that, there is the atmosphere. Pluto has one, thin, fragile, barely there by any earthly standard, but real, measurable, and chemically complex. It consists primarily of nitrogen, with traces of methane and carbon monoxide, all three of which sublime transition directly from solid ice to gas when Pluto moves to the closer portion of its elongated orbit and receives slightly more solar warmth. That atmosphere extends hundreds of kilometers above the surface and interacts with the solar wind in ways that cause it to gradually escape into space over time. Carried away particle by particle into the void. When New Horizons looked back at Pluto after its closest approach, it photographed the atmosphere in silhouette against the sun, a thin, luminous haze surrounding the dark disk of the planet, layered and structured, glowing with scattered sunlight in bands that indicated distinct chemical strata, an atmosphere on a world at -230 degrees Celsius, so cold that most of what forms the atmosphere spends most of the year frozen solid on the ground. Pluto broke the model, but Arrokoth buried it. Arrokoth formally designated 2014 MU69, nicknamed Ultima Thule, before a more permanent name was assigned, was the second target of New Horizons after Pluto. On January 1st, 2019, the spacecraft made its closest approach to Arrokoth at a distance of approximately 6.6 billion kilometers from the Sun, the most distant object any human-made spacecraft has ever visited in the history of space exploration. It traveled there from the Pluto encounter over more than 3 years of additional flight, crossing billions of additional kilometers of the outer solar system, sending back data from a point so remote that radio signals from the spacecraft took more than 6 hours to travel back to Earth. The shape of Arrokoth was unlike anything previously seen. 2 lobes, one larger, one smaller, joined at a narrow neck, the whole thing resembling a flattened peanut or a snowman lying on its side. The larger lobe, named Wenu, and the smaller lobe, named Yo, are clearly distinct bodies. They once existed separately, orbiting the Sun in paths close enough to each other that their gravities gradually drew them together, not in a violent collision, not in the kind of high-speed impact that blasts material in all directions and reshapes both objects catastrophically, but in a slow, gentle approach over vast spans of time. They drifted toward each other, matched velocities, touched, and stayed together. A contact binary, formed through the quietest possible mechanism. That gentle merger carries enormous scientific weight. For decades, the dominant model of how planets formed from the primordial disk of gas and dust held that growth happened through energetic collisions, small objects smashing into each other at high speeds, some sticking, others shattering. The survivors gradually accumulating mass through a process of chaotic attrition. The competing model, known as pebble accretion, proposed something different, that under the right conditions, material in the early solar disk could concentrate and clump through gentler gravitational attraction, objects drifting together slowly, rather than colliding violently. The two models made different predictions about what the oldest, most pristine objects in the solar system should look like. Arrokoth settled the debate. Its shape is only consistent with gentle accretion. A violent collision at the speeds typical of the early solar system would have shattered both lobes or created a surface geology full of the evidence of impact craters, fractures, asymmetric deformation. Instead, Arrokoth's surface is smooth, its color uniform across both lobes, its contact neck structurally intact. Two objects that came together slowly, without violence, and merged so gently that 4.6 billion years later, you can still see exactly where one ended and the other began. Arrokoth was the first direct observational evidence for pebble accretion, not a theoretical argument, not a computer simulation, but a physical object carrying the record of its own formation, preserved in the deep cold of the outer solar system since before Earth existed. There is a moment worth returning to, not a data point, not a measurement, a photograph. The image New Horizons sent back of Pluto in approach, showing a crescent of sunlight along one edge, and below that illuminated crescent, mountains of water ice rising white and sharp against a sky of absolute black. No atmosphere visible in that image, no haze softening the edges, just mountains, and silence, and a darkness so complete it has no equivalent anywhere on Earth. even on the clearest night in the most remote place imaginable. The mountains looked sharp, clean, almost delicate, and impossibly, inexplicably alive because mountains require geological processes, and geological processes require energy. And energy at 5 billion kilometers from the sun shouldn't be enough. But there they were. That was the first time science had produced that feeling lonely and astonished at the same time, not one or the other both, simultaneously and inseparably bound together. If Pluto, more than 5 billion kilometers from the sun, still has active geology, what does that say about the worlds even farther out? But New Horizons didn't only change the way we see Pluto, it changed the entire way humanity understands the solar system. New Horizons launched on January 19, 2006. At the moment of separation from its upper stage rocket, it was moving at approximately 58,000 kilometers per hour, the fastest spacecraft ever launched from Earth at that point in history. Not fast enough to outrun light, not fast enough to cross interstellar distances in any reasonable time frame, but fast enough that if you placed it on the surface of Earth and pointed it in a straight line, it would circle the planet at the equator more than once every minute. By the standards of anything humanity had ever built and thrown into space, it was extraordinary. It didn't stay at that speed. It got faster. In February 2007, 13 months after launch, New Horizons made a close pass by Jupiter, not to study Jupiter, but to steal from it. The technique is called a gravitational slingshot, and it works by threading a spacecraft through the precise gravitational geometry of a massive planet in such a way that the planet's orbital momentum transfers, partially, to the spacecraft. Jupiter, moving through its own orbit at roughly 47,000 kilometers per hour, effectively gave New Horizons a push. The spacecraft emerged from the Jupiter encounter, moving approximately 14,000 kilometers per hour faster than it arrived. Total velocity after the slingshot, more than 72,000 kilometers per hour. Jupiter lost an immeasurably tiny fraction of its own orbital energy in the transaction. New Horizons gained years. Without that Jupiter assist, the journey to Pluto would have taken 3 to 4 years longer. With it, New Horizons was on a trajectory that would bring it to Pluto in the summer of 2015, 9 years after launch. Give or take the month, 9 years. Hold that number alongside the velocity 72,000 kilometers per hour, sustained continuously. No stops, no slowdowns, no fuel burned after the Jupiter flyby except for minor course corrections. 9 years of that. And the destination was not some distant star or the edge of the galaxy. The destination was Pluto, which sits at an average distance of roughly 39 astronomical units from the Sun. Still inside the solar system, still by cosmic standards, practically next door. In those 9 years between launch and arrival, things happened on Earth. A child born the week New Horizons launched was finishing middle school and entering high school by the time the spacecraft finally reached its target. Smartphones went from novelty to ubiquity. Multiple national governments changed hands. Entire industries appeared, peaked, and declined. The world that New Horizons left behind in January 2006 was a recognizably different place from the world that waited for its transmissions in July 2015. The spacecraft moved through none of that. It simply flew silently through the dark, crossing distances that don't have intuitive human equivalents, closing in on a target it couldn't see for most of the journey. The closest approach happened on July 14th, 2015. New Horizons passed within approximately 12,500 kilometers of Pluto's surface, closer than some artificial satellites orbit Earth. Close enough that Pluto filled the spacecraft's cameras in a way that turned a blurry dot into a world. The entire close encounter, the period during which the spacecraft was near enough to Pluto for high-resolution observation, lasted only a matter of hours. There was no option to linger. New Horizons was moving too fast for Pluto's gravity to capture it. And the mission designers had always known this. The spacecraft would sweep through the Pluto system like a stone thrown past a target, cameras and instruments firing in every direction, recording everything possible in the narrow window before the planet fell behind. During that closest approach, New Horizons was not in contact with Earth. It couldn't be the spacecraft's instruments, and its communication antenna couldn't point in different directions simultaneously. And pointing the antenna at Earth during closest approach would have meant pointing instruments away from Pluto. The mission controllers had made their choice months in advance: science first, communication later. New Horizons flew past Pluto in autonomous silence, following preloaded instructions, making every observation on its own without any real-time human input possible. The reason was distance. Radio signals travel at the speed of light, and the speed of light covers the distance between Pluto and Earth in approximately 4.5 hours one way. That means any instruction sent from Earth took 4.5 hours to arrive. Any data sent from New Horizons took 4.5 hours to reach home. There was no possibility of real-time communication, no way for the control team in Laurel and Maryland to watch the encounter as it happened and make adjustments. By the time any signal from the spacecraft arrived, confirming that the closest approach was underway, the closest approach was already over. By the time the mission team received confirmation that everything had worked, New Horizons had already been flying away from Pluto for 4.5 hours. That gap, the 4.5 hours between event and knowledge, is not a technical inconvenience. It is a direct physical consequence of the solar system's scale. The team knew intellectually that the spacecraft was fine, that the approach was proceeding as planned, because they had tested and retested and simulated every step of the sequence. But knowing intellectually and receiving confirmation are different things. And the hours before that confirmation signal arrived were, by multiple accounts from mission scientists, among the longest hours of their professional lives. When the signal finally came through a simple carrier tone indicating that New Horizons was alive, had completed its observations, and was ready to begin transmitting data, the control room erupted. Not because anything had gone wrong and been recovered, because 9 years had passed, and the spacecraft had worked, and something that had existed only as plans and calculations and engineering drawings in January 2006 had just become history. The data transmission that followed tested patience in its own way. New Horizons had collected 6.25 gigabytes of data during the Pluto encounter images, spectroscopic readings, atmospheric measurements, particle counts, magnetic field observations. 6.25 gigabytes is not a large number by the standards of any device built in the 21st century. A modern smartphone holds many times that in a single folder of photographs, but transmitting 6.25 gigabytes across 5 billion kilometers through a spacecraft antenna with a transmission power roughly equivalent to a household light bulb, to receivers on Earth that had to be among the most sensitive ever built just to detect the signal at all, that took 16 months. 16 months to download the full record of a few hours at Pluto, arriving in pieces, each piece requiring 4.5 hours just to make the journey. The last images didn't arrive on Earth until late 2016. In that sense, the Pluto encounter didn't fully end until more than a year after it began. 9 years to arrive, a few hours at the destination, 16 months to receive the results. If it took 9 years just to reach Pluto, the nearest edge of the Kuiper Belt, how long do you think it would actually take to explore the full extent of what lies beyond? But the travel time is not the largest problem here. The larger problem is what New Horizons actually found, because what it found forced science to rewrite the history of planetary science entirely. Before July 2015, the scientific picture of Pluto was honest in its limits. Astronomers knew Pluto's approximate size, its mass, its orbital parameters, the existence of its largest moon Charon, and the basic fact that its surface contained some combination of ice and rock. What they couldn't know, what no instrument available before New Horizons could resolve from Earth's distance, was the surface itself, the texture, the geography, the chemical variation, the presence or absence of geological features. From Earth, Pluto was a smear of pixels, a blur of reflected light that yielded averages rather than details. Scientists had models, they had reasonable hypotheses. The working assumption, the one that felt consistent with everything known about cold, distant, airless worlds, was that Pluto's surface would be roughly uniform in ancient, battered terrain covered in craters accumulated over billions of years of bombardment, geologically dead, frozen in the state it had reached early in the solar system's history, and unchanged since. That picture was not wrong because scientists were careless. It was wrong because the universe had not yet shown them what it was actually doing out there. The first high-resolution images from New Horizons showed at least 5 distinct terrain types on Pluto's surface, not minor variations in crater density or surface texture, but categorically different geological environments sitting adjacent to each other, separated by sharp boundaries, each one telling a different piece of a story that nobody had anticipated. Rugged mountain ranges, smooth plains, heavily cratered ancient terrain, pitted, irregular terrain that suggested sublimation ice, converting directly to gas and leaving behind hollows in the surface, and stretching across a significant portion of the hemisphere facing Charon, the enormous pale expanse that would be named Tombaugh Regio, the heart-shaped region that became the most recognizable feature of Pluto in every photograph published afterward. At the western edge of Tombaugh Regio sits Sputnik Planitia, the nitrogen ice plain whose implications keep compounding the longer you examine them. It covers an area larger than the state of Texas. Its surface is smooth to a degree that stands out immediately in any image conspicuously, almost unnaturally smooth, unmarked by the craters that pepper every other ancient surface in the solar system. The absence of craters is the tell. Craters accumulate over time. Every impact leaves a mark, and the older a surface, the more marks it carries. A surface with almost no craters is a surface that has been recently renewed, geologically speaking, recently enough that subsequent impacts haven't had time to accumulate. Sputnik Planitia's surface, by this analysis, is no older than perhaps tens of millions of years in a solar system that is 4.6 billion years old. Something is resurfacing it. The leading explanation is convection nitrogen ice within the basin is being warmed very slightly from below by Pluto's residual internal heat, causing it to rise, spread across the surface, cool, and sink again in a cycle that turns the entire basin over on timescales of hundreds of thousands of years. The polygon patterns visible across Sputnik Planitia's surface, each polygon hundreds of kilometers across. Their boundaries slightly raised where convection cells meet are the visible signature of that process. Pluto is not sitting still. Its interior retains enough heat to drive movement in the ice above it, and that movement is ongoing. Beyond Sputnik Planitia, nitrogen ice flows, not in the liquid sense at Pluto's temperatures. Nothing flows in the way water does on Earth. But nitrogen ice under sufficient accumulation behaves plastically, deforming under its own weight and creeping slowly downslope over geological time, filling valleys, pooling in low terrain, carving channels in the landscape as it moves. New Horizons captured evidence of these nitrogen glaciers in multiple locations. Tongue-shaped flows of bright ice extending from highland regions toward lower terrain, their surfaces showing the same convection polygon texture as Sputnik Planitia. The mechanics are different from terrestrial glaciers. The timescales are longer. The temperatures are incomparably colder, but the process is recognizable. Ice flowing under gravity on Pluto. Then there is Charon, which had its own surprises entirely independent of Pluto's. Charon is large enough relative to Pluto. Its diameter exceeds half of Pluto's own diameter, that the two objects are genuinely a binary system, both orbiting a common center of mass that sits outside Pluto's surface. No other planet-moon pair in the solar system has this relationship to the same degree. They are, in every gravitational sense, partners rather than parent and satellite. Charon's surface carries a feature that has no clean parallel anywhere else in the solar system. At its north pole lies a large, dark, reddish region designated Mordor Macula, a stain covering a significant portion of the polar cap, far darker and more saturated in color than anything else on Charon's otherwise gray and white surface. The explanation for Mordor Macula involves a process that operates across the space between two worlds. Pluto's thin atmosphere leaks methane gas escaping from Pluto's surface, drifts outward into space. Some of it intercepted by Charon's gravity and deposited at Charon's poles, where temperatures are cold enough to freeze it onto the surface. Once frozen there, Pluto's methane ice on Charon's pole is exposed to ultraviolet radiation from the sun and to cosmic rays, which break apart the methane molecules and reassemble their components into complex organic compounds, the same tholins found throughout the Kuiper Belt. Over millions of years, these compounds have built up into the dark reddish crust visible at Charon's North Pole, one world chemically feeding another, across a gap of nearly 20,000 kilometers, producing something visible from billions of kilometers away, a process that nobody had hypothesized before the images arrived, because nobody had imagined that the atmosphere of one object could meaningfully interact with the surface of its companion at that scale. If a supposedly dead world like Pluto still holds this many surprises, imagine what larger objects sitting deeper in the Kuiper Belt might be hiding. New Horizons didn't stop at Pluto. After the Pluto encounter in July 2015, the spacecraft kept moving because it had no choice, and because the mission team had planned for exactly this. While New Horizons was still transmitting its Pluto data back to Earth in fragments over those 16 months, scientists were already directing the spacecraft toward a second target, a small thus distant object that had been selected precisely because it lay along the trajectory. New Horizons was already flying. The object was designated 2014 M-69. It had been discovered only in 2014 using the Hubble Space Telescope, found specifically because the mission team needed a Kuiper Belt object reachable from New Horizons' existing path. They found one, just barely. On January 1st, 2019, New Horizons made its closest approach to 2014 MU-69, later formally named Arakoth, from a word in the Powhatan language meaning sky at a distance of approximately 6.6 billion kilometers from the Sun. That number deserves a moment. 6.6 billion kilometers. It is the farthest point from Earth that any spacecraft has ever conducted a dedicated scientific encounter with a specific target. Not a flyby of something incidentally nearby, not a distant observation from afar, a close, deliberate, instrument-focused investigation of an object chosen in advance, at a distance that makes the Pluto encounter seem almost local by comparison. The images that came back were unlike anything in the archive of planetary science. Arakoth is small, roughly 35 kilometers at its longest dimension, which puts it in an entirely different size category from Pluto. But its shape is what arrested attention immediately. Two lobes, fused together at a narrow neck, the whole structure resembling a flattened peanut or a child's drawing of a snowman seen from the side. The larger lobe, named Wenu, connects at the neck to the smaller lobe, named Waio. They are clearly distinct objects. The boundary between them is visible not just in the shape, but in the subtle differences in surface texture at the contact zone. These two pieces did not form as one, They formed separately, and then they came together. How they came together is the story that changed everything. The older model of planetary formation, the one that dominated textbooks for decades, held that the early solar system was a violent place. The primordial disk of gas and dust surrounding the young sun was populated by countless small objects moving at high relative velocities, colliding, shattering, some fragments re-accreting into larger bodies. The survivors gradually growing through a process of chaotic attrition. In this model, the building blocks of planets grew by smashing into each other at speeds high enough to generate heat, deform surfaces, and leave unmistakable evidence of violent impact histories. The surfaces of early solar system objects, under this model, should carry the scars of that violence-fractured terrain, asymmetric deformation, the telltale geology of repeated high-speed collisions. The competing model, known as pebble accretion, told a different story. It proposed that under the right conditions in the early solar disk, material could concentrate through gentle gravitational attraction rather than violent collision. Small objects drifting in the same region of the disk, orbiting at similar velocities, could gradually feel each other's gravity, slow their relative motion, and drift together over long periods of time, not crashing, but settling. The merger, when it finally happened, would be slow enough to leave both objects largely intact, their original surfaces preserved, their contact zone showing the marks of a gentle union rather than a catastrophic impact. Arakoth is the physical proof that pebble accretion is real. Everything about Arakoth's shape and surface is consistent with gentle accretion and inconsistent with violent collision. The two lobes are intact. Neither shows the deformation that a high-speed impact would produce. No flattening on the contact face, no debris field surrounding the neck, no compression features radiating outward from the merger point. The neck connecting Wennu and Weo is narrow but structurally coherent. The kind of contact zone you get when two objects drift together slowly enough that their surfaces simply rest against each other, rather than slamming and rebounding. The geometry of the whole object suggests that Wennu and Weo once orbited each other in a shared orbit, a binary pair slowly spiraling inward under the influence of their mutual gravity and the gentle drag of the surrounding disk material, until their orbits decayed enough to bring them into contact. Not a collision, an embrace that took millions of years to complete. Then there is the color. Arakoth's entire surface is the same reddish-brown tone uniform across both lobes, uniform across the contact neck, uniform across every region that New Horizons cameras could resolve. That uniformity is scientifically extraordinary. Any significant impact after the object formed would have excavated fresh material from beneath the surface, exposing subsurface ice or rock with a different composition and a different color from the radiation-processed outer layer. The impact record would show up as color variation bright patches where fresh material was exposed, darker patches where different chemistry accumulated. Arakoth has none of that. Its surface looks the same everywhere because nothing has disturbed it since it formed. No major impacts, no geological resurfacing, no process that reached down and brought up new material. What sits on the surface of Arakoth today is what was there when the solar system was new. The reddish tholins coating both lobes formed in the early solar disk and have been sitting undisturbed ever since, preserved in cold that stopped chemical change before it could begin. Arakoth is not just an old object. It is an unmodified object, a sample of the primordial solar disk preserved in a state of near-perfect integrity for 4.6 billion years. Did you catch that? We just looked at the stem cell of the solar system, intact after 4.6 billion years. But if Arakoth is a stem cell, then what is the entire Kuiper Belt, and how far does it actually extend? The classical definition places the Kuiper Belt between 30 and 50 astronomical units from the Sun. That range appears in textbooks, in scientific papers, in every general explanation of the outer solar system. It has the feel of a settled fact, a boundary that has been measured and confirmed and can be stated with confidence. 30 to 50 astronomical units. Start at Neptune. End somewhere past the halfway point between Neptune and the theoretical location of the inner Oort cloud. Clean, defined, finished. Except the boundary at 50 astronomical units is not where the Kuiper Belt ends. It is where our ability to easily detect things begins to fail, and beyond that detection limit lies one of the most puzzling features of the outer solar system, a feature that current models cannot explain and that points insistently towards something unknown. It is called the Kuiper Cliff. At approximately 50 astronomical units from the Sun, the density of Kuiper Belt objects drops sharply, not gradually. Not in the slow thinning that you might expect from a population of objects simply spreading out over a larger volume of space sharply, in a way that looks less like a natural edge and more like something swept the region clean. Below 50 astronomical units, KBOs are distributed in patterns that models of the early solar system can account for reasonably well. Beyond 50 astronomical units, the population essentially vanishes. The cliff is not an artifact of observational bias alone. Astronomers have accounted for the fact that objects are harder to detect at greater distances, and the drop-off is steeper than detection limits explain. Something reduced the population of objects in that region, and the leading candidate for something is a planetary body large enough to gravitationally scatter objects out of that zone over billions of years. A planet nobody has found yet. Beyond the Kuiper Cliff, the outer solar system continues in a region called the scattered disk, which extends to well over 100 astronomical units and contains objects whose orbits were disrupted, scattered outward by gravitational interactions with Neptune during the early solar system's turbulent history. Scattered disk objects share their origin with Kuiper Belt objects, but travel on highly elongated orbits that take them far beyond the main belt and then swing them back in. Their paths shaped by gravitational encounters that happened billions of years ago and left permanent marks on their trajectories. The scattered disk and the classical Kuiper Belt are not cleanly separate structures. They overlap in origin, in composition, in the objects that populate their outer edges, and in the questions they raise about what shaped this part of the solar system. Then there is Sedna. It deserves its own category. Sedna is a dwarf planet, reddish, small, cold in the way that everything at its distance is cold, but its orbit is what makes it scientifically alarming. At its closest approach to the Sun, Sedna comes into approximately 76 astronomical units. That alone puts it well beyond the classical Kuiper Belt's outer edge. But Sedna's orbit is not circular. It is elongated to a degree that has no parallel among known objects in the solar system. At its most distant point, Sedna travels approximately 937 astronomical units from the Sun deep into territory that no spacecraft has ever visited, deeper than the scattered disk, approaching the inner edge of the hypothetical Oort cloud. Its orbital period is somewhere around 11,000 Earth years. Sedna is so far from everything that it takes longer than all of recorded human history, multiplied by several times over just to complete a single orbit. No known planet can explain Sedna's orbit. The gravitational influence of Neptune, Jupiter, or any of the other 8 confirmed planets cannot account for an object being nudged into an orbit that elongated, that extreme, that far from the plane of the solar system's main activity. The orbit implies that something pushed Sedna or pulled it into that path, something with enough gravitational mass to reach out to those distances and reshape an object's trajectory. Whatever that something is, it hasn't been found. Sedna is not alone in having a strange orbit. A cluster of smaller KBOs in the outer solar system share orbital characteristics that shouldn't align by coincidence. Their orbits are tilted and oriented in ways that cluster together when they should. statistically, be distributed randomly. In 2016, astronomers Konstantin Batygin and Michael Brown at Caltech ran the numbers on this clustering and published a paper proposing an explanation: a planet undetected, with a mass approximately 5 to 10 times that of Earth, orbiting the Sun at a distance somewhere between 400 and 800 astronomical units, on an orbit tilted relative to the main plane of the solar system. They called it Planet 9. The probability that the orbital clustering of the known objects occurred by random chance, they calculated, was approximately 0.007%. That is not a discovery. There is no image, no direct detection, no confirmed sighting. Planet 9 is a hypothesis supported by statistical inference, the gravitational shadow of something whose presence is felt in the orbits of other objects without the object itself having been seen. But the inference is not weak, and the alternative explanations that the clustering is a statistical artifact, that observational bias accounts for it, have not fully held up under scrutiny. There is something out there, or there isn't, and the instruments that might resolve the question are only now coming online. Science, it turns out, doesn't only close mysteries. Sometimes it opens them. Every answer the Kuiper Belt has provided has arrived with 2 or 3 larger questions attached. The boundary was supposed to be at 50 astronomical units. Then the Kuiper Cliff appeared and asked what caused it. Sedna appeared and asked what shaped its orbit. The orbital clustering appeared and asked what is out there in the dark at 400 to 800 astronomical units, massive enough to bend the paths of worlds. The pattern is consistent and humbling. The more carefully anyone looks at the outer solar system, the less finished it appears. And the real boundary of the solar system, if one exists at all, lies somewhere that even New Horizons has not come close to reaching. The solar system that exists today is not the solar system that formed 4.6 billion years ago. That statement sounds like it should be obvious. Of course, things change over billions of years, but the degree of change and the violence of the process that produced the current arrangement is something that took decades of careful work to establish. For most of the 20th century, the working assumption in planetary science was that the planets formed roughly where they are now, settling into their current orbits early in the solar system's history and staying there. The solar system was seen as a structure that had found its equilibrium and held it stable, ordered, essentially fixed. That picture was dismantled by a set of computer simulations published in 2005 by a group of researchers working primarily in Nice, France. The model they produced, known ever since as the Nice model, pronounced to rhyme with geese, described a solar system whose early history was far more turbulent than anyone had formally proposed before, and whose planets did not stay where they formed. The Nice model begins with the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, positioned significantly closer to the Sun than they are today, all sitting within a much more compact region of the early solar system. Beyond them lay the primordial disk of planetesimals, the raw population of icy and rocky bodies from which the Kuiper Belt is the surviving remnant. In the Nice model's sequence of events, gravitational interactions between the giant planets and the planetesimal disk gradually destabilized the planetary orbits over hundreds of millions of years, eventually triggering a period of dramatic orbital reshuffling. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward, substantially outward, crossing orbital resonances with each other in a cascade of gravitational interactions that sent Uranus and Neptune into the outer solar system where they sit today. As Neptune migrated outward, it plowed through the primordial disk, scattering billions of objects, flinging some inward toward the Sun and the inner planets, pushing others outward into what became the scattered disk, and capturing others into resonant orbits that locked them into the rhythmic gravitational relationship With Neptune, they still maintain today. The Kuiper Belt, under this model, is not a pristine relic sitting untouched where it formed. It is the surviving remnant of a disk that was dramatically sculpted by Neptune's outward migration, thinned, sorted, and reorganized by the gravitational wake of a planet moving through it over millions of years. The structure visible in the Kuiper Belt today carries the fingerprints of that migration, and those fingerprints were what allowed scientists to test the NEAS model against observation. The test worked. The orbital distribution of Kuiper Belt objects, the specific ways their orbits cluster at certain distances, tilt at certain angles, and align in certain patterns, matches, with striking fidelity. The predictions of computer simulations modeling Neptune's outward migration, not approximately, not in general trend, in specific quantitative detail that would be extraordinarily unlikely to arise from any other process. The Kuiper Belt's architecture is, in this sense, a recording of what Neptune did, a frozen record of a planet's journey written in the orbits of everything it disturbed along the way. Nowhere is this more clearly written than in the Plutinos. Plutinos are a specific population of Kuiper Belt objects sharing a particular orbital relationship with Neptune for every 2 orbits Neptune completes around the Sun. A Plutino completes exactly 3. This is called a 2 to 3 orbital resonance, and it is not coincidence. Objects in this resonance receive gravitational nudges from Neptune at regular, repeating intervals, nudges that, over long timescales, reinforce the resonance rather than breaking it, keeping the objects locked in that rhythmic pattern indefinitely. Pluto itself is a Plutino, so are hundreds of other confirmed KBOs. The resonance protects them from close encounters with Neptune by ensuring that whenever a Plutino is at the part of its orbit nearest to Neptune, Neptune is always somewhere else. These objects didn't wander into that resonance on their own. Neptune swept them there. As Neptune migrated outward through the primordial disk, it carried its resonances with it like a net, capturing objects along the way and dragging them into synchronized orbits. The Plutinos are the trapped catch populations of objects that Neptune gathered during its migration and locked into gravitational step with itself, where they have remained ever since. They are not just evidence that Neptune migrated. They are the direct, physical record of how far it traveled and what it collected along the way. The consequences of Neptune's migration for the inner solar system were catastrophic, at least temporarily. The disruption of the primordial disk sent an enormous flux of objects, icy bodies from the outer solar system, rocky bodies from the inner disk on new trajectories that crossed the paths of the terrestrial planets, Earth, the Moon, Mars, Mercury, Venus. All of them were struck repeatedly during this period in an event recorded in the cratered surfaces of every airless body in the inner solar system. The Moon's highlands are saturated with impact basins from this era. Mars carries ancient scars of the same bombardment. Even Earth, whose active geology has erased most surface evidence from that period, shows chemical and isotopic signatures in its oldest rocks consistent with a massive influx of extraterrestrial material roughly 4 billion years ago. This episode is called the Late Heavy Bombardment. Its timing, approximately 4 billion years ago, fits the chronology of the NEAS model's predicted orbital instability, the connection between Neptune's migration, the disruption of the Kuiper Belt's precursor population, and the subsequent rain of impactors onto the inner solar system has become one of the most compelling through lines in the entire history of planetary science. A chain of cause and effect linking the outer solar system to Earth's surface, with the Kuiper Belt as the reservoir from which the projectiles came. What those projectiles carried matters enormously. Kuiper Belt objects are not inert rock. Their composition includes water ice, carbon compounds, nitrogen ice, and the complex organic molecules, the tholins. the amino acid precursors that form when simple chemistry is exposed to radiation over geological time in the cold of the outer solar system. When these objects struck the early Earth during the late heavy bombardment, they didn't just carve craters, they delivered material, water, carbon, organic compounds, the building blocks of the chemistry that eventually, after billions of years of further processing, produced the first living molecules. Earth's oceans are a problem that planetary science has worked on for decades. The water on Earth's surface has a specific isotopic signature, a specific ratio of ordinary hydrogen to the heavier isotope deuterium, and that signature doesn't perfectly match the water in the rocky asteroids of the inner solar system, which were the obvious nearby candidates for Earth's water delivery. It does, however, overlap with the isotopic signature of water ice found in comets and KBOs from the outer solar system. The match is not perfect, and the debate about exactly what fraction of Earth's water came from where is ongoing. But the contribution of outer solar system objects from the Kuiper Belt and its precursor population to Earth's water budget is scientifically credible, supported by geochemical evidence, and increasingly difficult to dismiss. Amino acids have been found in meteorites, not every meteorite, and not in concentrations anywhere near what biology produces, but present, formed through abiotic chemistry in the cold and radiation of space, surviving the heat of atmospheric entry, landing on Earth as molecular seeds. The Kuiper Belt, with its rich inventory of organic compounds frozen and preserved for 4.6 billion years, was likely a significant source of that kind of material during the bombardment period. If the water on Earth came from the Kuiper Belt, where did our life actually begin? But the question of life's origin is only a small piece of the larger picture. The larger piece lies in what remains entirely unknown. Every catalog has a limit. Every map has an edge beyond which the cartographer simply ran out of information and stopped drawing. The maps of the Kuiper Belt that exist today, the ones listing confirmed objects, plotting their orbits, describing their surface compositions, represent something that looks, from a distance, like substantial scientific knowledge. More than 2,000 confirmed objects with documented orbits, dozens studied in detail, surface compositions analyzed, sizes estimated, moons detected. It sounds comprehensive until you ask a simple question. What fraction of what's actually out there does any of that represent? The answer is uncomfortable, deeply, structurally uncomfortable. To map the Kuiper Belt completely defined and catalog every object down to some reasonable minimum size, you would need to survey the entire sky systematically, repeatedly, with instruments sensitive enough to detect objects at distances of 40 to 50 astronomical units. The full sky covers approximately 41,000 square degrees. The Kuiper Belt doesn't span the entire sky, but its disk-like distribution means that a thorough survey requires covering hundreds of thousands of square degrees of sky at the sensitivity levels needed to detect faint, slow-moving objects against the background of stars. That is not a weekend project. It is not a decade project with conventional instruments. It is an undertaking that, until very recently, was simply beyond what any telescope on Earth could accomplish in any realistic time frame. The constraint is sensitivity combined with scale. The most powerful ground-based telescopes currently operating can detect Kuiper Belt objects with diameters of approximately 100 kilometers or larger at distances of 40 to 50 astronomical units, provided those telescopes are pointed at the right patch of sky at the right time, and provided sufficient observing time is allocated to confirm that a moving dot of light is actually a KBO rather than a background artifact. 100 kilometers is not a small threshold. Objects below that size and the population of smaller KBOs vastly outnumbers the large ones. Following the same size distribution that governs populations of small bodies everywhere in the solar system are simply invisible to current ground-based surveys at Kuiper Belt distances. They exist, The physics requires them to exist in enormous numbers, but they cannot be seen. The James Webb Space Telescope, which began science operations in 2022, has started probing the Kuiper Belt with capabilities that ground-based observatories cannot match. Its infrared sensitivity and the absence of atmospheric interference allow it to detect smaller and fainter objects than any ground-based instrument. Early results have been promising, identifying objects that would have been entirely invisible to previous telescopes. But Webb was not designed primarily as a solar system survey instrument, and its observing time is divided among an enormous range of scientific priorities: distant galaxies, exoplanet atmospheres, stellar nurseries, the cosmic microwave background. The fraction of Webb's time dedicated to Kuiper Belt survey work, however valuable, is not sufficient to produce the comprehensive census that the belt's scale demands. The instrument that carries the most realistic near-term hope for transforming the Kuiper Belt catalog is the Vera-C Rubin Observatory in Chile, designed specifically for wide-field survey astronomy. The Rubin Observatory's legacy survey of space and time is engineered to photograph the entire visible sky repeatedly over a 10-year baseline, building a dynamic map of everything that moves: asteroids, comets, KBOs, near-Earth objects, transient events of every kind. When operating at full capacity, it is expected to discover hundreds of thousands of new Kuiper Belt objects, potentially increasing the known catalog by a factor of 10 or more within the first few years of operation. Objects that have been invisible to every previous survey: too faint, too small, too far, will begin appearing in the data stream in quantities that will require automated systems just to process the volume. Even that will be incomplete. Rubin sensitivity still has limits. Objects below a certain size at Kuiper Belt distances will remain undetected. The true population, including every object, down to the scale of a few kilometers, may never be fully enumerable with any instrument operating from Earth's surface or Earth's orbit. Conservative estimates place the number of KBOs with diameters exceeding 100 kilometers at a minimum of 70,000. When smaller objects are included, the total population of the Kuiper Belt climbs into the hundreds of millions. Some models suggest it may reach into the billions when the full-size distribution is accounted for. Billions of objects. Confirmed catalog, roughly 2,000. The ratio is not a rounding error. It is a statement about the current state of human knowledge, not a temporary gap that will be closed next year or next decade, but a structural limitation imposed by the combination of distance, object size, and the practical constraints of survey astronomy. Standing at the edge of what the current catalog represents and looking toward what lies beyond it is not like looking at a map with some blank spaces. It is like standing on the Atlantic coast, watching a few fish break the surface and declaring that the ocean has been surveyed. The fish that jump are real. The survey is not. And if we barely know anything about the Kuiper Belt itself, what lies beyond it is a mystery that runs incomparably deeper. The Kuiper Belt does not end cleanly. Nothing in the outer solar system does. What sits beyond the classical belt's 50 astronomical unit edge is not empty space waiting to be categorized. It is a series of overlapping regions, each less understood than the one before it, each carrying populations of objects whose orbits raise questions that current gravitational models cannot fully answer. The scattered disk comes first. Its objects originated in the same primordial disk that produced the classical Kuiper Belt. But Neptune's outward migration during the early solar system's turbulent history sent them onto highly elongated orbits, stretched, tilted, reaching far beyond the main belt before swinging back in. Scattered disk objects spend most of their orbital time at enormous distances from the Sun, but their elliptical paths occasionally bring them back into the region where Neptune can interact with them gravitationally, further perturbing their orbits over time. The scattered disk extends to beyond 100 astronomical units and contains objects that are, in many ways, more dynamically interesting than classical KBOs precisely because their orbits are still evolving. They are not settled. They are still being pushed around by the gravitational machinery of the outer solar system. Beyond the scattered disk, things become genuinely strange. Sedna and a small but growing group of objects, known as detached objects, occupy orbits that are disconnected from Neptune's gravitational reach in a way that the scattered disk's objects are not. Their closest approaches to the Sun are too far away for Neptune to have placed them there. Neptune's gravitational influence does not extend to 76 astronomical units, which is Sedna's perihelion distance. Something else shaped those orbits, something that acted on these objects either in the early solar system or is acting on them still. They are detached from the planetary system in the most literal gravitational sense. No known planet can claim them, explain them, or account for their trajectories. They drift in a region of the solar system that existing models describe poorly, on orbits that point towards something undiscovered, farther still so far that direct observation has never confirmed a single object. There lies the inner Oort cloud, sometimes called the Hills cloud. It is entirely hypothetical in the sense that no object has been definitively identified as belonging to it, though Sedna and 2012 VP-113 are candidates for its inner edge. The inner Oort cloud is theorized to occupy the space from approximately 2,000 to 20,000 astronomical units from the Sun, a vast, spherical reservoir of icy bodies too distant for current instruments to resolve, too slow in their orbital motion to be detected against background stars in any reasonable observing campaign, too far for any spacecraft launched in any human lifetime to reach. It exists in models. It exists in the mathematics of comet dynamics. Whether it exists in the sky the way the Kuiper Belt exists in the sky as a real, physical population waiting to be cataloged is something that has not been confirmed by direct observation. Beyond the inner Oort cloud lies the Oort cloud proper, not a disk, not a belt, a sphere, a vast, roughly spherical shell of icy bodies surrounding the entire solar system at distances from approximately 2,000 to 100,000 astronomical units from the Sun. Its outer edge approaching the gravitational boundary where the Sun's influence gives way to the influence of neighboring stars. The Oort cloud is where long-period comets come from, the ones that fall inward toward the Sun on orbital paths that take hundreds of thousands or millions of years to complete. Occasionally disturbed by a passing star or the gravitational tide of the Milky Way galaxy itself, and sent on trajectories that bring them into the inner solar system for the first time in their existence. A comet appearing in Earth's sky with an orbital period of 1 million years has spent essentially its entire existence in the Oort cloud, falling inward for the very first time. Its one visible pass is, in every meaningful sense, its debut. There is a smaller bubble nested inside all of this. The heliosphere, the region of space filled with the Sun's solar wind. The constant outflow of charged particles streaming outward from the Sun at hundreds of kilometers per second extends to a boundary called the heliopause, where the solar wind pressure finally balances against the pressure of the interstellar medium pushing back. That boundary sits at approximately 120 to 130 astronomical units from the Sun. Voyager 1 crossed it in 2012. Voyager 1 was launched in 1977. It took 35 years of continuous flight at roughly 61,000 kilometers per hour to cross from Earth to the heliopause to exit the Sun's immediate physical environment and enter the space between the stars. It is the most distant human-made object in history. Currently, more than 160 astronomical units from the Sun and receding at a rate that will take it to 200 astronomical units sometime in the coming decades. The heliopause is not the edge of the solar system. By the measure of gravitational influence, by the presence of the Oort cloud, The Sun's domain extends 1,000 times farther than where Voyager 1 now travels. The heliopause is simply the edge of the Sun's breadth, the point where the solar wind stops. The Sun's gravity continues far beyond it, holding the Oort cloud in its embrace across distances that make the heliopause seem like the end of a front porch. If Voyager 1 launched in 1977, the farthest object humanity has ever sent into space has only just crossed the heliopause. When could we ever reach the Oort cloud? The answer is with current technology. Never. And that exposes an unsettling truth about the limits of what humanity can reach. For most of the 20th century, the solar system was treated implicitly as a special case. Not special in any mystical sense, scientists don't work that way, but special in the practical sense that it was the only planetary system available for detailed study. And the assumptions built from studying it carried an unexamined bias that what we had here was, if not unique, at least particular to our circumstances. The Kuiper Belt, the asteroid belt, the arrangement of planets, the distribution of debris. These were the solar system's specific features, products of its specific history, not necessarily representative of anything broader. That assumption began dissolving in the 1990s, and by the time the Hubble Space Telescope and later the James Webb Space Telescope turned their instruments toward nearby stars, it had collapsed entirely. What those telescopes found around other stars were debris disks, flattened rings, and shells of dust and icy material. Orbiting at the outer edges of other solar systems, detected through the infrared light, they emit as dust grains absorb starlight and re-radiate it as heat, and in some cases, visible directly as scattered light in Hubble's optical images. These disks are not identical to the Kuiper Belt. They vary in size, in density, in composition, in how they are structured. But they are recognizably the same category of thing, the leftover material from planet formation, preserved at the outer edges of a stellar system in a region too cold and too sparse for planets to fully assemble. Held in orbit by the gravity of the star at the center, Fomalhaut is one of the most studied. It sits approximately 25 light-years from Earth in the constellation Piscis Austrinus, close enough, by stellar standards, that Hubble could image its debris disk in visible light with enough resolution to show its structure. What those images revealed was a narrow, sharply defined ring of material, orbiting Fomalhaut at a distance comparable to the Kuiper Belt's position around our own Sun, but with a total width and radius nearly twice as large. The ring's inner edge is surprisingly sharp, not the gradual thinning you would expect from material. Simply spread across a range of orbits, but a clean boundary that implies something is clearing the inner region. Something with enough gravitational influence to sweep the space inside the ring. Relatively free of debris, and maintain that sharp inner edge against the tendency of orbital mechanics to blur it over time. A planet. Most likely one that has not been directly imaged, but whose presence is written in the shape of the ring it has sculpted. Fomalhaut's debris disk is not an accident or an anomaly. It is a mature stellar system, showing the same broad architecture as the solar system a star. Planets implied by their gravitational effects on surrounding material, and an outer belt of remnant debris marking the edge of the region where planets formed and the beginning of the region where they didn't. Beta Pictoris offers a different view of the same phenomenon. Seen at an earlier stage, it is a young star only approximately 20 million years old, a fraction of the solar system's 4.6 billion year age, surrounded by a disk of gas and dust that is still in the process of sorting itself into a planetary system. The disk around Beta Pictoris is enormous, extending hundreds of astronomical units from the star, and it is not smooth. It shows warps, asymmetries, and gaps that indicate planetary bodies already forming within it and gravitationally disturbing the surrounding material. A directly imaged planet, Beta Pictoris b, orbits within the disk at a distance comparable to Saturn's distance from our Sun. Another candidate planet sits closer in. The disk itself is the solar system's analog state, what the region around our Sun looked like 4.6 billion years ago, before the planets had fully formed and cleared their orbits, when the primordial disk was still the dominant structure and everything was still in the process of becoming. Beta Pictoris is not showing us another solar system. It is showing us our own solar system's past, frozen at a moment we can no longer observe directly. Epsilon Eridani sits closer than either Fomalhaut or Beta Pictoris, only 10.5 light-years from Earth, making it one of the nearest stellar systems with a confirmed debris disk structure. It is older than Beta Pictoris, old enough that its disk has had time to settle into something more organized. And what has emerged is a system with not one, but two distinct debris belts. One sits at a distance comparable to the asteroid belt between Mars and Jupiter in our own solar system. The other, farther out, occupies a position analogous to the Kuiper Belt. Between them and beyond the outer belt, the distribution of material implies the presence of at least one large planet. Shaping the gap between the two rings, the same gravitational architecture that Neptune provides in our own solar system, sweeping the region between the inner planets and the outer belt, maintaining the structure through gravitational influence rather than physical presence. Epsilon Eridani, Fomalhaut, Beta Pictoris, 3 different stellar systems at 3 different stages of evolution, all showing the same basic pattern: outer debris ring, implied planet shepherding the boundary, structure imposed on material that would otherwise spread and blur. The pattern is not coincidental. It is the expected outcome of planet formation physics operating in any system where planets form in a disk around a star and the outer regions retain their primordial material. The Kuiper Belt is not an exception. It is the rule. Most mature stellar systems, as far as current observations can determine, possess an outer debris region analogous to what surrounds our own Sun. The variation is in the details: the size of the ring, its distance from the star, the sharpness of its edges, the composition of the material. But the basic architecture repeats across the stellar neighborhood with a regularity that carries a significant implication. When searching for life elsewhere in the universe, the instinct is to focus on planets the right size, the right distance from the star, the right temperature range for liquid water. That focus is reasonable. But what the prevalence of debris disks suggests is that the search cannot stop at the planet. The outer regions of a stellar system, the debris disk, the cold belt, the reservoir of primordial material, are part of the same system, and they participate in the history of every planet within it. They delivered water. They delivered organic compounds. They shaped planetary surfaces during bombardment epochs. They carry the chemical record of what the system was made of before any planet existed. A planet without its outer belt is a body stripped of its context. The outer belt is not the edge of the story, it is part of the story's foundation. This means that when searching for life beyond Earth, looking only at planets is looking at only part of the picture. The full system, including its outer edge, must be considered. But if every star system has its own Kuiper Belt, then the greatest mystery is no longer our own. In January 2016, 2 astronomers at the California Institute of Technology published a paper that did something unusual in modern planetary science. It proposed the existence of a new planet in the solar system without having observed one. Konstantin Batygin and Michael Brown being the same astronomer whose discovery of Eris had triggered Pluto's reclassification a decade earlier, were not speculating casually. They had done the mathematics, run the simulations, examined the orbital data, and arrived at a conclusion that they found difficult to avoid. Something large was out there, something that had not been found. The evidence was orbital. 6 Kuiper Belt objects in the distant outer solar system. objects with highly elongated orbits, taking them far beyond the classical Kuiper Belt's edge, shared an unusual characteristic. Their orbits were clustered, not randomly distributed across the sky as the orbits of uninfluenced objects should be, but tilted and oriented in the same general direction, grouped together in a configuration that seemed to point toward a single gravitational source. The probability that this clustering arose by random chance, Badigian and Brown calculated, was approximately 0.007%. That is not zero, but it is close enough to zero that explaining it as coincidence requires rejecting the statistical reasoning that underlies most of planetary science. The explanation they proposed was a planet undetected, far out, massive enough to gravitationally herd those distant KBOs into their aligned configuration through billions of years of subtle orbital perturbation. Their estimates for its properties, derived from the orbital data of the affected objects and from dynamical modeling of how large a perturber would need to be to produce the observed clustering, converged on something roughly 5 to 10 times the mass of Earth. Not a gas giant on the scale of Jupiter or Saturn. Something more like a super-Earth or a small Neptune, a planet of a type extremely common around other stars but not previously confirmed to exist in our own solar system. Its estimated distance from the Sun ranged from approximately 400 to 800 astronomical units, putting it far beyond anything previously mapped in detail. On an orbit so large that a single circuit around the Sun would take between 10,000 and 20,000 Earth years to complete. If Planet 9 exists at those parameters, it is larger than Earth, significantly larger. It would be, unambiguously, the 9th planet of the solar system, restoring a 9th member to the planetary roster from which Pluto was removed, but replacing the small, icy dwarf with something genuinely planetary in mass and gravitational influence. It would also be a planet that has been present in the solar system for billions of years, quietly shaping the orbits of distant objects, leaving its gravitational signature in the architecture of the outer solar system, without ever having been seen by any telescope ever pointed at the sky. The skeptics arrived with their own analysis. A study published in 2021 examined whether the apparent orbital clustering of those 6 key KBOs might be an artifact of observational bias rather than evidence of a real gravitational influence. The argument ran as follows: astronomers don't survey the entire sky equally. Certain regions are observed more frequently than others, for reasons of accessibility, instrument scheduling, and historical survey priorities. If the surveys that discovered those 6 objects happened to concentrate on particular parts of the sky, the orbits of the discovered objects would naturally appear clustered in the direction those surveys emphasized, not because anything was gravitationally herding them, but because that's where astronomers happened to look. The 2021 paper argued that when observational bias was accounted for carefully, the statistical significance of the clustering diminished substantially, and the case for Planet 9 weakened. The debate has not been resolved. Both sides have continued refining their analyses. The pro-Planet 9 camp has pointed to additional lines of evidence: the extreme orbit of Sedna, the peculiar orbital tilts of certain trans-Neptunian objects, the overall architecture of the outer solar system's population as independently supporting the presence of a large, distant perturber. The skeptics have continued pressing on the bias question, arguing that the data are not yet sufficient to distinguish between a real gravitational influence and a sampling artifact. As of 2024 and into 2025, the question remains genuinely open. Planet 9 is neither confirmed nor ruled out. The instrument that may finally settle it is the Vera-C Rubin Observatory. Its legacy survey of space and time will survey the sky with a systematic thoroughness and sensitivity that no previous program has achieved. Discovering enormous numbers of new outer solar system objects across a much wider and more uniformly sampled area of sky than the surveys that produced the original clustering evidence. If the clustering persists and strengthens as the sample of known distant KBOs grows to thousands, the bias explanation becomes increasingly difficult to sustain. If the clustering dissolves as new objects fill in the gaps, the case for Planet 9 weakens accordingly. Either outcome is scientifically valuable. Either outcome will be decisive in a way the current data cannot be. The Rubin Observatory is expected to deliver its answer within the first few years of full operation. Until then, Planet 9 remains a gravitational ghost present in the mathematics, absent from the images, neither real nor dismissed. If there is a planet larger than Earth hiding in our own solar system, one that has been there for billions of years, shaping the orbits of distant worlds, and we have simply never found it, what does that say about the limits of what we currently know? But whether Planet 9 exists or not, there is something more certain, and it is more unsettling than any hidden planet. Count the missions. It doesn't take long. 2 spacecraft have traveled through the Kuiper Belt with any scientific intent. Voyager 1 and Voyager 2, launched in 1977, passed through the region on their way out of the solar system, but they were not sent there. They were sent to Jupiter and Saturn, with Voyager 2 continuing to Uranus and Neptune. The Kuiper Belt was simply the space they crossed afterward, and they crossed it without instruments designed to study it, without the ability to target specific objects, without the resolution to image anything they passed at the distances involved. They flew through. They did not explore. New Horizons is the only spacecraft ever designed specifically to study the Kuiper Belt. One mission, launched in 2006. It reached Pluto in 2015, visited Arakoth in 2019, and is now continuing outward into the deeper belt, still returning limited data from instruments growing older with each passing year, still transmitting across distances that make every signal a small miracle of engineering. One spacecraft, one set of instruments, one trajectory through one narrow corridor of a structure containing hundreds of millions of objects distributed across billions of kilometers of three-dimensional space. Hold that against the rest of what humanity has done in space. 6 crewed landings on the Moon, multiple robotic rovers on Mars, with more planned, orbiters around Mercury, Venus, Jupiter, Saturn, landers on the surfaces of asteroids, a probe that flew through the atmosphere of Jupiter, a spacecraft that intentionally crashed into a comet. The inner solar system has been visited, prodded, sampled, and photographed from dozens of angles by dozens of missions spread across 6 decades of spaceflight. Mars alone has hosted more dedicated scientific missions than the entire Kuiper Belt has received in all of human history. The disparity is not a matter of neglect or lack of interest. It is a matter of distance. And distance in the outer solar system is not a problem that ambition or funding can solve on its own. With current propulsion technology, chemical rockets, gravitational assists, where available, reaching the outer edge of the classical Kuiper Belt at 50 astronomical units takes approximately 15 to 20 years of continuous flight, not 15 to 20 years with a stopover, not 15 to 20 years with any realistic option to slow down and enter orbit around a target, 15 to 20 years of straight-line travel at the fastest speeds current technology can produce, arriving at the destination still moving too fast to stop, able only to observe for the brief window before passing through and continuing outward. To reach Sedna at its closest approach to the Sun, approximately 76 astronomical units, would require more than 25 years of uninterrupted flight. Under the same conditions, a mission duration longer than many scientific careers, longer than the gap between the Apollo landings and the launch of New Horizons itself. And those are the reachable targets. The Oort cloud, beginning at approximately 2,000 astronomical units from the Sun, sits at a distance that current spacecraft speeds make effectively unreachable within any single human lifetime. New Horizons travels at roughly 58,000 kilometers per hour. At that speed, covering 2,000 astronomical units, the inner edge of the Oort cloud would take approximately 700 years. Not a generation, not a century. 700 years of continuous flight to reach the nearest boundary of a structure that extends to 100,000 astronomical units on the other side. The far edge of the Oort cloud, at 100,000 astronomical units, would require New Horizons approximately 35,000 years to reach if it were aimed there and if it survived that long, which it would not. These numbers are not failures of engineering. They are statements of physics. The solar system is large in a way that resists correction by better technology, by larger budgets, by more determined engineers, even light traveling at nearly 300,000 kilometers per second. The absolute speed limit of the universe needs more than 8 hours to cross from the Sun to the outer edge of the Kuiper Belt at 50 astronomical units. Light needs weeks to reach the inner Oort cloud. Light needs more than a year to reach the outer Oort cloud. Nothing moves faster than light. Nothing ever will. The barrier is not what humanity knows or what humanity wants. The barrier is what the universe permits. And the universe has built a solar system so large that the species living on the third rock from the Sun, after decades of spaceflight, after everything achieved and everything attempted, has managed to send one dedicated mission through a narrow slice of the region sitting just beyond its own planetary neighborhood, and that mission is still considered one of the greatest achievements in the history of exploration. The Kuiper Belt is the greatest test of humility the universe has presented to humanity. Not because it is dangerous, not because it threatens anything, but because it reveals how small we remain despite how far we have come. Every achievement in space exploration, every rover, every lander, every orbital insertion, every gravitational slingshot calculated to perfection has taken place within a tiny fraction of the volume of the solar system that the Kuiper Belt alone represents. Everything humanity has ever physically touched in space fits inside the inner region, the part closest to the Sun, the part that the Kuiper Belt dwarfs in sheer extent and almost certainly in sheer number of objects. Knowing that most of our own solar system remains a mystery, how does that change the way you look at the night sky? Throughout everything covered here, the false boundary at Neptune, the frozen archive of ancient chemistry, the geological surprise of Pluto, the stem cell simplicity of Arakoth, the invisible gravitational influence of a possible ninth planet, the debris disks orbiting other stars. The Kuiper Belt has been described as the outer region, the far part, the edge of the solar system beyond which the real unknown begins. That framing is wrong, and the correction is not a minor adjustment. The Kuiper Belt is not the outer edge of the solar system. It is the innermost layer of the part that has never been explored. Consider what sits beyond it. The Oort cloud, if it exists as theorized, and the behavior of long-period comets provides strong indirect evidence that it does encloses the entire solar system in a spherical shell, so enormous that comparing it to the Kuiper Belt requires the word millions. The Oort cloud's estimated volume exceeds the Kuiper Belt's by factors that make the comparison almost meaningless as a numerical statement. Its outer boundary, at approximately 100,000 astronomical units from the Sun, sits at a distance of roughly 1 to 2 light years, not astronomical units. Light years, the unit used to measure distances between stars, the unit that belongs to interstellar space rather than planetary science. 1 to 2 light years. Proxima Centauri, the nearest known star to the Sun, is approximately 4.2 light years away. That means the outer Oort cloud extends more than halfway from the Sun to the nearest star. Not approaching it, not close to it in the way that Pluto approaches the edge of the planetary region. Actually halfway there in terms of raw distance, sitting in territory that has always been described as the empty void between stellar systems, the interstellar medium, the space between things, the nothing that separates one solar system from the next, except it is not nothing. The Oort cloud is something, a vast, spherical population of icy bodies, loosely bound to the sun by gravity attenuated across distances that beggar description, drifting in orbits so large that most of them will never complete a single circuit in the remaining lifetime of the sun. These objects belong to the solar system in the sense that they orbit the sun rather than any other star, but they exist in a region of space that no human instrument has resolved, no spacecraft has visited, no catalog has begun to populate. They are hypothesized from the behavior of the comets. They occasionally release comets that fall inward from those enormous distances, taking tens of thousands or millions of years to complete their first approach to the inner solar system, arriving as visitors from a region of the solar system so remote that their existence there was inferred before it was even theoretically formalized. Here is what that means for the picture of interstellar space that most people carry. The gap between the solar system and Proxima Centauri, 4.2 light-years of what appears, from any diagram ever published, to be empty space is not empty. If the Oort cloud extends 1 to 2 light-years from the sun, and if Proxima Centauri has its own equivalent structure, which the physics of planetary formation strongly suggests it should, then the outer clouds of these two stellar systems are not separated by a vast gulf. They are close to each other. They may overlap. Right now, while every human being alive goes about their day under the assumption that the space between stars is a featureless void, the outermost halos of two neighboring stellar systems may be interleaved icy bodies from the sun's cloud drifting through the same region as icy bodies from Proxima's cloud. The two populations mixing in territory that no one has observed and no instrument currently operating can resolve. The boundary between our solar system and the next one is not a line. It is not even a gradient with a clear midpoint. It is a zone of ambiguity, a vast, cold, dark region where the influence of one star fades and the influence of another strengthens, where objects that formed around the sun and objects that formed around other stars may share the same orbital neighborhood without any instrument anywhere being able to tell them apart. The solar system doesn't end at Neptune. It doesn't end at the Kuiper Belt. It doesn't end at the heliopause, where the solar wind stops and interstellar space begins. Even that boundary is a boundary only for the sun's wind, not for the sun's gravity, not for the sun's family of orbiting objects. The question of where the solar system truly ends, of where our star's dominion gives way completely to something else, does not have a clean answer. It may not have any answer at all. The transition may simply be too gradual, too diffuse, too interwoven with the equivalent transitions of neighboring systems to locate at any specific distance. So look up tonight. Find the brightest star visible from wherever you are standing. Hold the distance in mind, not the number of light years, which is too abstract to feel, but the fact of it. Between the ground beneath your feet and the light entering your eye from that star, there is no empty space. There are billions of frozen objects, ancient and silent, drifting in the dark, unnamed, unseen, unstudied, and in all likelihood, never to be understood within the span of human civilization as it currently exists. They formed when the solar system formed. They have been there ever since. They will still be there, unchanged, when everything built by human hands has long since ceased to exist. They are not far away in the way that other galaxies are far away, or in the way that the cosmic microwave background is far away. They are here, part of this solar system, this neighborhood, this stretch of space that humanity has spent centuries learning to call home. The terrifying reality of the Kuiper Belt is not that it is vast, or cold, or ancient, or full of things we don't understand. The terrifying reality is simpler and quieter than any of that. We live inside something we have barely begun to see,